Hi.
Can you see me? Can you hear me? Right.
Yeah,
Okay.
we can hear you.
Okay. My audio is working. Well, I'm pleased to see you all. And how many do I have in the class? Just give me a second. Wow. It's 43 and counting. Very good. Very good. Just give me a second. I wanted to open my Canvas page. Should take another moment. Come on. Almost there. There we are. All right. Yesterday we were talking, it was an introduction, and after that I sent you, did you see my email on our, not email, but text on the chat in Teams? I put a scary message that from yesterday noon up to evening today, you have 1.5 working days, which is 8 + 4, 12 hours of continuous full-time work. Right, it was actually quite a serious message. The thing is that since they switched our teaching and learning mode to block teaching, we have to be quite aware of the time. And well, my job is to occupy you with videos and any sort of tasks and so on full time. Those hours have to be occupied. So hopefully by today you managed to review a few topics from discrete event models in the lecture material. Am I right? Well, I don't see your faces, and well, it's quite difficult to have this set up to see everybody's face, and many of them are just hiding behind the avatar. And at the same time, look at the shared material. So please shout when I ask. So did you manage to have a look at the discrete event models?
Just a few.
Just a few.
Yeah, same, just a few.
Yeah.
Right, so let's establish the extent of those few. This is the plans. Presumably you started with the beginning. There was something about reactivity, FSM, and FSM, 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 and then Petri nets, right? And Petri nets, they go through the whole topic, and Petri nets is the main model, which we use to model concurrent programs. And with the use of this model, we explain what it means to have a critical section, what it means to use a mutex somewhere, and so on. What it means to have certain effects in a program related to concurrence. So the Petri nets, it's the main kind of target. But before starting with Petri nets, I suggest here to start with this, which is finite state machine, and it's prerequisite, right? And Petri net is very similar to a finite state machine, with the difference that new components are added to the model, and as a result, the model becomes more rich. It can capture more things. So presumably you started with the beginning, and how far did you advance? Did you have a look at Petri nets building blocks for models? There are some animation slides there. Did you reach this?
No, not yet.
Yeah, even I stopped right before that. Sorry.
Yeah.
Oh, you stopped here. Okay,
Yes, yes.
fine. So we will progress then from the definitions and the sense behind Petri nets. to the building blocks. And the difference between the two topics is that first, we need to somehow make sense of what Petri nets are, and then learn here to build systems as models. You see, so you have a specification in words, right? Then you scratch your head and you need to first model it somehow, then make sense of a model, and then decide what paradigms to use in programming, in the design of the system. Right? So that's the design part, which is probably missing as you haven't touched this just yet. But first we need to start with Petri nets because this is for the benefit of the silent part of the class. And I'm suspecting that many of them would benefit from this. So let me download and open. Download it, open system view, and need to reshape the window. Need to hide side panel, mode not continuous. Right. And I need to share it because I'm sharing the wrong window. Right. Those in the class who would like me to roll further back to the finite state machine, please shout now. And if you don't, then I will not roll back.
Could you come again, Alex?
Well, coming again. So I am addressing those who are the silent majority of the class. Those who want me to go further back in our history towards the previous kind of set of slides and the talk, which is prerequisites, reactivity, FSM, and so on. If you want me to start with that, I can start with that. Otherwise, I will start with the part 2 of the topic because a request was made and I was told that actually this is where some of you have finished the revision.
Well, I see most of the C programs, I mean, are based on this Petri nets on the problems, and better we have to start from here.
Okay.
I'm fine. Yeah.
Okay, fine. So I'm sure that you are probably on the side of the most advanced kind of learners who moved quite far away forward. I'm usually concerned about those who are silent. But anyway. So the idea here is to start with this slide, actually. So the idea is to introduce a new model, which is a Petri net. A Petri net. And how we introduce it? On the left, I have an example of a finite state machine. Finite state machine, it's this graph. Right? And the previous lecture, which is recorded and so on, and I had no questions about this as I prompted. It's about this kind of models, right? And we want to modify it to something which looks like this. And apparently the left and the right models as drawn here do the same thing. They're equivalent. The drawing is slightly different, but they're equivalent. So the purpose of complicating this drawing on the right is to show that the new model does the same as finite state machines, but also has new added features. So we need to start with complete equivalence, and then we will add something new to this. All right. So what is added? In the finite state machine, we have states. And we have a token sitting in one state. It's the initial state marked like this. And then the token can move along the arcs, and the arc is called a transition. And it will move from here to here, for example, right? And from here, it may move either here or there, depending upon whether we are firing B or D, B transition or D transition, right? At the moment, I am not saying what controls the movement of the token. I'm saying that at this point, there is a choice to go here or there. And then it may move somewhere and will start traveling around. And all this thing resembles a board game. So you have a drawing of this board game and the token, and you move the token around, and the token marks the state which is currently active. And the components of this model are states, transitions, the initial state, and when it's moved further, then it becomes the current state, not the initial. The initial is just where we are starting everything. And we also have labels, A to E, right? Why do we need labels? Why not? It's just easier like this, and you can associate labels with something complex, such as you can say that if label B equals to 1, then we fire this transition. If D equals to 1, we fire this transition. So you can add new kind of interpretations to the model based on the labels. Okay, so yeah, that's the internet. So what we do here, we draw additional nodes, those bars, in the middle of each transition. And now the transition becomes a node. So in this model, a transition was an arc. Here, a transition is a node, similar to a state, right? And instead of saying that this is a state, we say that these are a place. You see, we replace the word state with the word place. Why do we replace it? Because you will see later that in a Petri net, we can put a token here, and potentially we can put another token there. So you can have several tokens. And the combination of the tokens in the network will be called later a state. And so each individual location of the token has to be called with a different name. Therefore, the name is chosen, a place. Now, why do we need this vertical bar? Why do we need this new node here? Because later you will see that sometimes we will have several arcs escaping from the same transition. So one of them is going here, and the other may go somewhere else, right? And by splitting such a transition, having kind of several outputs of this transition, we will increase the number of tokens. So the input token arrives here and then becomes split. Something goes here, something goes there. And as a result, we can start multiple movement of multiple tokens in the system. They will be moving independently from each other. So they will be concurrent, right? And here we need to explain what the word concurrency means. Concurrency means. Well, concurrency, it was kind of hinted in the previous set of slides. Concurrency means lack of order. Hand waving helps. In a finite state machine, everything happens in a full order. First this thing, then this thing, then this thing, then this thing. By saying a thing and moving my hand like this, I mean that it is an event of some sort. If you can say that after this event happens, this means that there is an order. So they're connected. In order to fire the second one, I need to fire the first one. Between them, there is a causal order. This one causes this one. It's causality. The word causality is important. Please write it down. It's all about causal relationships, right? In a finite state machine, causality, it's an arc, which is a transition. In Petri nets, causality is expressed through flow relationships, those arcs, which are similar to transitions in finite state machines. They're also aligned with an arrowhead causality. Now, what is concurrency? Concurrency is if you have two transitions, my left and right arm, and it may happen that they fire or are executed in the order like this. This one is the first.
That's when he falls.
The second. Or they may execute in the opposite order. This one is the first and this one is the second. And I have no idea in which order they will be executed. And then I say that they're independent from each other because I cannot establish in which order they execute. Therefore, they're concurrent. It may easily happen that this one executed and this one is not executed. So this one has to be executed multiple times before this one becomes executed. So no relationship. So concurrency, it's lack of relationship, no relationship. It is the concept which is the opposite of order. Now let's go back. In our first model here, model of Petri net, we do not have any concurrency. Why? Because the idea was to repeat the same functionality as a finite state machine. And in finite state machines, we don't have concurrency, so here we also don't have concurrency. So the idea here was just to show that we can have the same functionality in a Petri net compared to an FSM. After that comes a definition. A definition occupies 1 page, 2 pages. And then comes the illustration. So please bear with me. There will be 2 pages of mathematics, and after that there will be an animation. A Petri net is defined as a tuple. Tuple means it's a collection of symbols. That's the tuple, right? And for no apparent reason, it's called sigma altogether. Well, that's the tuple. What does this tuple include? It includes several symbols, P, T, F, and M0. These are all symbols in uppercase. In uppercase, in the theory of sets, we usually denote sets. So P is a set, T is a set, F is a set, M0 is a set as well. Right? I am assuming that you are reasonably okay with the definition of a set. It comes from your prerequisites. If you wish, we can go back to the basics of mathematics and talk about sets. Sets are collections of elements with certain properties. Now, what are those sets? P is a set of places. And this set includes these elements. Elements are lowercase. Sets are uppercase. And how many elements do we have here from 0 to k, right? So it will be k plus 1 probably. Places in our drawings are denoted as circles, like this. Where are they? These are places. Places. Place can be marked or can be not marked. And how many we have them? 1, 2, 3, 4. Therefore, there will be P0, P1, P2, P3, right? So it's a set of places. We have another set here, T. Its transitions is defined as curly brackets, and here we have enumeration of elements, transitions from T0 to Tn, and they denoted as, I cannot select this, as a bar. So these are transitions. I don't care at the moment how transitions are related to places. I'm just saying that there are places and there are transitions, and each of them is a node or a vertex of our graph. So far, there is no meaning behind this. It's just a description of the drawing. So it's a graph where we have two types of nodes. One type is places and the other type is transitions. Places are usually circles and transitions are usually bars or squares. So far, so good. The next is this thing, arrow. Arrow, those arrows. What do they mean? The arrows mean which node follows which, right? Which one follows which. They call it flow relationship. We can also call it causality relationship. So one thing causes the other, or flow relationship. So how to understand this formula? Flow relationship, F, you see uppercase. Uppercase means it's a set. It's a set of what? Of those arrows. So flow relationship is not just a set, but it's also a subset of this. Now, what is this selected at the moment? It is a union of this thing and this thing. What are those things? In the brackets, I have P multiplied by T. P is a set, T is a set, multiplication, it's Cartesian product. A Cartesian product, from the mathematics point of view, it's a very simple thing. It's a collection of pairs of elements. So in each pair, the first element is picked up from here, from P, and the second from T. So it's a collection of pairs. Not just collection of pairs, but the first element comes from P, the other from T. And first, second are associated with the ends of this arrow. So the first is here, the second is there. So here we have all arrows which start at places and finish at transitions. So this set, going back, includes all arrows which start from a place and finish at transition, like this one, like this one, like this one, like this one. Good, right? What about starting from a place and finishing on this transition? It's not shown here. Not shown here. It's okay, that's not shown. It is still present in the selected area of the formula. But you remember, this sign means a subset. Subset means that those objects which are present here, they may or may not propagate into the F. So not all of them are selected. Right. Now, what does it mean, this one? It's a Cartesian product of T multiplied by P, right? So it's a collection of all those arrows which begin at T and finish at P. So those which begin at T at transition and finish at place, like this, like this, like this. But what about going from here to here? It's not shown, right? Not shown here. Why? Because it's not selected. because of this relationship. It's a subset. Subset means that whatever is included into this set, right, should belong to this set. But certain things which are included in this set may not find themselves in this one. So it is a subset. So this one on the right is a large set, it's a complete set. And here we have a small set, a selection. That's it. Does it make sense? Right.
Yep.
If it does not, then shout, and if it does, also shout, it's fine. Okay, so far so good, and we managed to describe places, transitions, and what is important in this formula. This formula does not include arrows which start from a place and finish at a place. It's only from place to transition, from transition to a place, but never from place to place. And it's never from transition to transition. Therefore, they call this graph, which we just obtained, a bipartite graph, or simply bigraph, right? So in our example, check any path like this or like this, any path, and you will have place transition, place transition, place transition, place transition along the path. It will never be place and suddenly place again. It will never be a transition and suddenly transition again. It will be a mistake. It will be a violation of the definition. So if you include an arc in your drawing, which connects a place to a place, then it's not our flow relationship. Therefore, it is not our Petri net, right? So it's as bad as it is. So if you make this mistake, then the comment will be, whatever model you produced, it is not a Petri net model. I may understand what you mean by this, but please be watchful. So far, so good. This is from here to here. It is the drawing of our board, and on the board we need to start playing the game. So we need to put tokens first and start moving tokens around. So tokens are those fat dots which are placed inside the places, like this. That is the token inside the place. And the token means that this place is marked. So they call it marking. Now let's look at the definition of the marking. First of all, the initial marking. So initially, some places are marked. It's this formula. The formula is long, but it is very, very simple. Marking is, I am translating from mathematical language. Marking is the following. Marking is a mapping of places into n, and n are numbers for counting stones, natural numbers, like 1 stone, 2 stones, 3 stones, or maybe 0 stones. The same is with tokens. 0 tokens, 1 token, 2, 3, 4, right? So basically, we can say that each place in the set of places have a number in it. And the number represents the number of those tokens in this model. In this place, how many tokens do we have?
0.
0, right? 0. And this one, 0. And this one, we have 1.
1.
And I have no single place where we had 2 tokens, or 3 or 4 or 5. All right. So it's the notation, very simple. Now we will be dealing with so-called one-safe Petri nets. Why? Because it's easier, and most important problems for our programming tasks can be solved on one-safe Petri nets. One safe Petri net means that place capacity. So you can maximum have in the place 1 token. You can have 0 or 1 token there. So it means that instead of this formula, we have to have a simpler one. N equals set, which one? This one. So we have either 0 or 1 token in each place. It's as simple as that. So we will be using one safety net soon. Right. At the moment, we have the board game. It's the drawing of the graph. We have arcs on it, so we know where to move our tokens, and we have the tokens placed strategically in the places, and we are prepared to start the game. But we need to know the rules of the game. The rules of the game are here. The other name for rules of the token game, it's semantics of the model. So let's look at the semantics of the model. Tokens move in the Petri net by firing transitions. The word fire is a term, and it is somewhere defined like this. And when you fire transitions, then tokens are moved into a new position. So initial position was where? Here. It was the initial marking. But after we have moved the tokens, it becomes the marking which is not initial, but the next one. So from the initial marking, we're arriving to a different marking, and then fire transitions arrive to a different marking again, and we go from one marking to the other, and all those markings which are reached from the initial transition are called reachable markings. However, it is just a model, and the model is perfectly suitable for showing how not to play the game. Right? So if you take a board game and make an incorrect move on it, and the figures cannot move like this, in chess, for example, checkers, or any kind of token game, right? Move them wrongly, it is a mistake, it's an error, right? And we can still represent this error by having an incorrect marking drawn. So this definition of a marking is rather generic. It says that we associate ends, which is 0 or 1, with each place. And this is exactly the same definition as for the initial marking, just it is not initial any longer. So at the beginning, this marking is called initial, but after that, it stops being initial. Does make sense? So this marking is just randomly placed tokens around the game, right? Among those markings, there will be some of them will be those which are reached from the initial marking, the so-called reachable markings. And some of them will be erroneous markings. And it's possible to say, I define an error in my system like this, and now let's check, is it possible that my system will arrive to this erroneous position? It will be a problem of verification. All right, enough discussion. Now we have defined a marking which is different from the initial marking. The next is to arrive to somehow to firing. And firing happens in 2 steps. First enable, then fire. And in order to enable, we need to define this preset and post set of a node. Right, so please bear with me. Preset of a node. Is depicted as dot and then the label of the node, X. Why is it X? Why is it not P? Why is it not T? Because I don't care whether it is a place or a transition. I can say that in the previous model here, that a preset of this node is what? going back through this arrow and say, okay, this transition is a preset of this node. What about this transition? A preset of this is this place. So if it is a place, then preset will be transitions. If it is a transition, the preset will be places. Right. Okay. So a preset of the node is another node and probably several other nodes, right? Such that, vertical bar means such that they are connected to the node in question. What is the node in question? X, right? That's one. The node in question is X, and Y sits in front of this in this pair, and the pair is in brackets. What is this pair? This pair, X and Y, comes from here or here, right? You remember the Cartesian products, these are pairs, they're ordered. So one element is taken from one set and the other from the other set, right? And the ordered means that they're written in brackets, comma separated, and one is the first and the second is the second. So the first is here, the second is there. That's the first, that's the second, that's the first, that's the second. Right? So the preset of node X, it's all those nodes which are before it, according to the flow relationship, and the flow relationship hits the arrow. So if you have X, which is a node, and you have several arrows pointing at that, then whatever the source of those arrows was, those nodes are included into this set, which is written in those curly brackets. Right? Of course, all these pairs, they belong to the flow relationship, and I said, as I said, those flow relationship is this one. It's a subset of these and these arcs. Okay, now post set of a node is roughly the same. Just you see the roles are changed now. It's all those y's which follow my favorite x, right? They're on the right. Here they were on the left. Here they're on the right. On the left means on this side. On the right means on that side. Right? So here we have a set or a collection of all those nodes which are directly after the selected node X. That makes sense? Please shout if it doesn't.
Yes.
Well, if you're scared to shout now, well, thank you for saying this, but for those who are afraid of shouting now, we can ask the question later as well. So it's just a structural definition, what is before and what is after a selected node, and the node can be either a place or a transition. So now we are prepared to do the most important part, which is actually learning how to move the tokens and how to play the games. So far, here it was just terminology. In the previous page, it was just a description of the board game, the structure of the graph, right? So this is the terminology. And from here, it begins the actual semantics. Right, okay, looking at the semantics. In order to fire a transition, we need to enable it. Okay, so in order to fire this transition, we need to enable it by placing a token there, right? And then the token will be moving between the places, so it will disappear from here, appear there, but the token will never sit inside this transition. This is why I drew transitions as bars. There is no space inside to draw a token. It's a convenient drawing. So a transition T which belongs to the set of transitions, of course, right? But just any transition, see, is enabled if its preset is filled with tokens. Okay, this transition, is it enabled? No, because its preset, where is the preset? Going backwards through the arc. Just one place is the preset. Is it filled with tokens? No, therefore this transition is not enabled. What about this? Should I move? No, I should move here, right? I need to go backwards through the arc and see, okay, this is my preset. Is it filled with tokens? Yes. Therefore, this transition is enabled. I can paint it red, or I can draw here star and say that this is the symbol, which means that it is at the moment excited. It's about to start firing. It's enabled. So the transition is enabled if its preset is filled with tokens. And you will see later that instead of one element in the preset, you can have 2 or 3 or many. Right? And sometimes they draw a star at the transition saying, okay, so you can see that it's enabled now. But you may draw it, may not. It depends upon the task which you are solving. After that, this statement comes. Enabled transitions may fire, or may not. All right. What does it mean? Let's assume that this is my transition. So I'm doing the transition with my right hand. And what I am trying to do, so if my left hand contains an object, a small screwdriver, right? Then with my right hand, I can grab it. And the action itself is a transition. And this transition is enabled if I have a condition that I have this screwdriver here. And then I start grabbing it, right? Now, prepared to grab, I have this screwdriver here. I begin kind of grabbing, so it's enabled, right? And then the screwdriver disappeared. Nothing happened. So if there is an alternative way for the token to disappear, you will see in the examples, it's easy to implement. Then the enabled transition may become disabled without firing. It's very interesting because in the physical system, enabled means that sometimes it means that we have started the movement already. We are about to grab it, and then the object just disappears. And then we have disappointment. We have this action which is incomplete, right? And if you start implementing a system with electronics, wires, and gates, it may result in a voltage, in a waveform which looks like a very narrow pulse, which appears and disappears before it becomes registered anywhere. So it's a glitch, it's interference, right? And unfortunately, such a glitch may go unnoticed or may become latched in memory elements. And
Sorry, sir.
it again.
If the translation is incomplete, then the glitch should be include the graph.
No, it is not included in the graph because we are talking about the graph, which is just a drawing. And separately, we are talking about semantics of how it is interpreted and how to play the token game, how to execute it, right?
Yeah, so the graph explains all complete transition, all right?
Well, yes. In the graph, we have complete transitions, and the graph is mathematical.
Yeah.
So I can show you this experiment with my my hand grabbing and missing it, right? So it's
Yeah.
incomplete action. In the electronics, there will be a glitch, pulse of voltage, error potentially, right? But in mathematics, it will not happen. Why? Because in mathematics, this happens in no time whatsoever. It's immediate, right?
Yeah.
And furthermore, you will see later that we have a so-called interleaving semantics. So we have one action at a time. So we will have to consider in mathematics two options every time. So it's either you grab it and you are happy with this, or the object has disappeared first and then you don't try to grab.
Oh
But
yeah.
yeah, so mathematics is different. In mathematics, we have perfect actions. What I'm saying that if you model like this, a physical system, then enabling means that you're already moving towards an action. And this kind of useless grabbing may happen.
Yeah, it's a physical action, but not expressing mathematics. Yeah, thank you, sir.
Absolutely, absolutely, absolutely. And you can probably find this in one of my do I have a lecture on, just give me a second. I had a lecture on a synchronization problem. It was probably removed. Taxonomy fix. Yeah, it is removed, but I will probably include it here, and it is a fun lecture to look at. It is more relevant to the microelectronics people. It's about building synchronizers and the situation where you are trying to grab and create this kind of useless action and potentially a spike of voltage in electronics. So it is. I have this lecture. It's an interesting problem and so on. Right. Meanwhile, I have to go back into the presentation slides. So this enabled transitions, they may fire or may not. In mathematics, it creates no problems, but in electronics or mechanical engineering, it may cause, they call it a hazard, an incomplete action. In general, when a transition is enabled and then disabled without firing and without any feedback, without any acknowledgement, then there is a potential problem with this. Now, the result of firing. I'm using the word enforces. Why? Because we are talking about mathematics. I don't want to say that I have a red Swiss knife here, right? And I do the action and the same red Swiss knife goes further. I don't want to say that this red Swiss knife is my token. No, a token is an abstraction. It's like flag. It says that in this place, the flag is up, you have a token there. Now the data moved further, now this flag goes down and the flag goes up here. So tokens are not interpreted as a physical object, which are objects which are moved, but they're indicators that there is something present or absent inside the place. Does it make sense? This is why it's wrong to say that it's the same token which goes there. No, this token just disappears, and on the right, the token just appears. So its flag goes down here, and here the flag goes up. All right, so hand waving sometimes is helpful. So this is why I'm saying that firing enforces what? In the preset of the transition, tokens disappear. So it becomes 0 tokens in each place, which is a preset. You see, it's a transition. So the preset of transition, it's one or several places. Does it make sense? Well, by the way, it doesn't need to be one. It can be no places whatsoever. Just a transition, nothing follows. I don't know how it works, but you can draw it. But the point is that in the preset of transitions, we are placing zeros, so no tokens. And in the post set of a transition, we are placing ones. So flags go down in the preset and flags go up in the post set. And therefore, we have new places marked now. So we are arriving to a new marking. It leads us to a new marking. So at first it was marking M, and now we have marking M dash. Right. And now I have this comment actually. Well, why I did this comment? Because we have a one safe Petri net. If it is drawn correctly, then this comment is not needed at all. Just remove it. And so if all your Petri nets are correct, then it's fine. However, if you draw your Petri net incorrectly, so the model is erroneous, it may attempt to put more than one token into the same place. So a token in the place, imagine it's sitting there and it didn't have a chance to go away. It's still sitting there, and the input transition fires again and adds the second token there, right? It should not happen in the one safe Petri net. So basically, it will mean that the Petri net is incorrect. And this kind of addition of tokens, and then we can arrive to 2 tokens, 3 tokens, and 4 tokens. It's a part of the theory of unbounded Petri nets, where you can put any number of tokens into a place. But this is not what we are looking at, right? So I decided to put here this comment because sometimes we will make mistakes and we will attempt to put more than one token in a place, right? And this is true for multi-valued or unbounded Petri nets. And the marking will be firing, and in the post set we will be adding new numbers. Does it make sense? So please ignore this in case that your Petri net drawing is correct, right? And this comment it only makes sense if your Petri net is of unknown quality, and by looking at it, by evaluating it, you want to determine whether it's correct or not. And one of the errors in constructing a Petri net is to try to do this +1. So it was 1, now it becomes 2. If it was 0, it becomes 1, it's fine. So this condition, -1 +1, will work with correct Petri nets. But if it is an incorrect, unbounded Petri net, then this will result in the numbers which are 0, which are different from 0 and 1. Does it make sense?
So the -1 and +1 show the state to express false or true.
Well, it is potentially possible to invent such a Petri net where you are forcing a transition to fire, and as a result, the number inside the place becomes -1. It will not be one safe. So it will be a violation of our class of Petri nets. Mathematically, it will be incorrect for one safe Petri nets. But it's possible to define such model. And the meaning of this -1 when you model a system will be that you are just borrowing.
Oh, yeah.
a token.
Mm.
So for example, if you have a semaphore in programming, right, it can be positive or negative or zero, right?
Yeah.
Because there is a count associated with this. So potentially it's not impossible to have it. I'm saying that we don't need it. And this comment is significant in order to distinguish between correct or incorrect unsafe Petri nets. Otherwise, I don't know how to explain that you should not try to put a token into a place before the previous token has gone. That's the reason why I put this token, why I put this comment here. So if it is unclear, I can return to this after showing the following examples. Because next is the animation. I spent some time, I'm proud of this, and let's have a look at this first, right? And for many of you, it will start making sense after you have looked at this. So this is just a drawing of the graph, and there is no marking whatsoever. So what is this? It's Petri net definitions, this page, right? Actually, M0 is missing there at the moment, so it's incomplete. It's incomplete. Now let's put here M0. This is the initial marking. Now we have a complete Petri net with the initial marking, and we can observe that certain places enable transitions. So this is a transition, painted red. Why is it painted red? Because it's preset. The preset includes just one place, this one, right? Its preset is filled with tokens, therefore this guy is enabled. This transition is also enabled. This transition is not. Why? Because the preset is empty. This transition is not. Its preset is where? This way and this one. So the preset is a set of two places, right? And the preset is empty, cannot fire. The same as here, cannot fire this, cannot fire that. Everything else is black. You see, only two transitions are enabled. Now let's fire those transitions. Are enabled. Is it possible for a token to disappear from here somewhere? No. The only way for the token to move is to execute this transition, and then marking will progress. Okay. Without any particular reason, I decided to fire both transitions at the same time. You will see later that we will put the restriction on this. So it will be the moment when we start drawing reachability graphs. So it is sufficient to observe behavior of a Petri net by firing one transition at a time. It's so-called interleaving semantics. Now, the token is here. Is this transition enabled? No. Why? Because its preset, where is the preset? That's the preset, right? Is it marked? No. It's halfway marked, halfway not. It's not filled with tokens. Therefore, this transition cannot fire. What about this? Yeah, it can fire, so it will fire. It fires like this. Now, this transition is enabled because it's preset. You can draw a shape around this, just oval, and say, okay, this is my preset. It's filled in with tokens. Therefore, this transition is enabled, and it will fire. I'm sure that will fire because these tokens cannot escape. There is no other way. There are no other arcs here. So it will fire. They call it join. It's the operation join. Why? Because here we had two threads of operation. They can run at different speeds. They are not dependent on each other, concurrent to each other. And this is the join operation. So this transition will be fired only once this thread and this thread have finished. So the tokens are here, therefore we can join two threads. The operation is join. Okay, it fires. And a remarkable thing happens. Look. we had 2 tokens and now we have just 1. So join operation has this remarkable ability to reduce the number of tokens in the system. So we reduce the concurrency. So instead of 2 threads, now we have just 1 thread running. Right? So these operations like join, choice, merge, fork, they are described in the next lecture in detail. So at the moment, I'm just giving this thing. Choice, yeah. This token can go one way or the other way because this and these 2 transitions are enabled. But apparently it cannot go both ways. Why? Because they call it interleaving semantics. So we need to consider firing 1 transition at a time. And this is a caveat which you need to remember. Right? And if this transition fires, then this token will disappear. This transition will stop being red, becomes black without firing. So it will be a situation when the transition is enabled, but then disabled again without firing. It will be a situation. Have a screwdriver. I'm just kidding. Take it. I'm just kidding, right? So the token is stolen. And it's stolen, why? Because we consider things in interleaving semantics. 1 transition fires at a time, not both at the same time. Okay, let's have a look how it happens. Without any particular reason, this transition fired, and this one became black. Token disappeared, appeared here, but this transition did not fire. So there is no token here. It's choice. Now the next is this transition is enabled and we are putting the token there. We call it merge operation. So it's either one or the other, but not together. It's one or the other thread are finished, never both together. And then the token gets there. It will be a mistake to have this and this, both threads running at the same time. Why? Because this one will try to put a token here and this one will try to put a token there, and it will be 2 tokens. It will not be one safe between it any longer. So merge operation always follows the choice. Merge always follows the choice, and choice does not increase concurrence. It's finite state machine-like operation. Okay, fine. All right. Now this transition is enabled for reasons that it is a preset. Now a remarkable thing will happen. So you see that's 1 token here. This operation they call it fork. It will fork 2 threads. They will start 2 threads, this one, and they're concurrent to each other. Look, 1 token disappeared, 2 of them appeared there. And after that, the tokens will run here and here independently from each other. So this operation is fork. Fork usually goes together with join because fork increases concurrency and join reduces concurrency. Choice does not change concurrency. It will be still the same thread, 1 thread. And merge does not change the amount of concurrency in your system. Now here, look, these 2 transitions are enabled. I can fire any of them at first. So let me fire this one. Right, that's the comment. This is taken from a cartoon, Simpsons, American series, with yellow people in it, and there is a man there who is always saying "do" because he's making mistakes. It's not really a mistake what I've done, but what I discovered that if you remember the first slide of animation, I departed from the initial marking where the token was here and another token was there, right? I have a system with a cycle. So I returned my activities back, but I missed the initial marking. I missed it because I fired this transition first. If I fired this one first, it would be exactly the initial mark, but I fired this transition first. I missed the initial mark. So apparently it's possible to have a system with a busy cycle, right? It starts with the initial marking, and it's possible to miss the initial marking due to the nature of concurrency. The concurrency means that we cannot guarantee that the order will be some particular order. The idea of concurrency is that we have two events, this and this, right? Either this happens first than this one, or this one and this one. And there is no way to tell which one is the first, which one is the second. The only way to describe it is to say that it can be either one option or the other option, and just have two traces recorded. Or maybe more than two, because there will be many more combinations between the multiple actions. So it is an interesting feature. However, if you continue the simulation, then at some point both tokens will arrive to this position. And I would argue that it's impossible to miss this marking. So this will be a marking where suddenly the concurrency disappears. It will be impossible to miss this marking. It will be possible to miss this marking because we can take potentially a different route because it's choice. So there are interesting features. The word reachable is used. Reachable means that we have departed from the initial marking here, and through many steps we have arrived to this marking, and this marking is clearly reachable. If I draw another fat dot here, it will be a mistake, right? Yes. And it will be a marking which is impossible or unreachable. We cannot reach such a marking by playing by the rules from the beginning of the game, from the initial marking. Still, it's possible to draw it, why not? So I can draw an error if you wish. That's how they do verification. They assume that you have a token here, here, and say, is it possible? And the verification tool tells you, no, it's not possible. That's the verification task. Why such a tool is needed? Because imagine that this model captures the behavior of a washing machine. And then you can ask the tool, is it possible to have a situation when you have the door to the washing machine open and the valve, water valve, also open, and the water is flooding the kitchen? And the tool will do the mathematics and will figure out and say, no, it's not possible. And then you're happy you can sell such a machine. If it says it's possible, then you have to fix the error in the design. Right, another example. So this one is a construction example. It has a meaning. It has a meaning in the sense that I would like here to introduce a way to communicate between different parts of the system, and you will see that we'll have to have a direct channel one way and the return channel, which is acknowledgement. It will be a handshake. Here we have two processes. The fat circle, large circle, means that here we are doing something important and producing some sort of a data. It's just a normal place. I just try to emphasize its meaning somehow, right? But from the point of view of Petri, that's just normal place. The same is here. So here we are consuming the data, and after that we can sit in a small circle and wait for the further actions. Right? So here we have producer. So the producer manufactures the data, and here we have a consumer. Consumer eats the data, consumes the data in this place. Now we need to connect somehow these two parts. How to connect them? Obviously, that after the master process has finished producing the data, it fires this transition, right? So this transition is a signal which should allow us to move the token from here to there, right? How to do that? Well, fork.
Maybe we need to enable flags, but slave should
Yeah.
be, yep.
Yeah, we can do the flags, but we can draw things. And the next picture actually will show that we implement these flags in drawing like this. So basically this transition fires, it produces a token sits here, and this token will enable this transition. And after that, this transition will fire. So the idea is at the beginning, this transition is enabled, this transition is enabled, but I want to slow down this transition. I want to make it wait until we have finished the business here and fired this. So I need some sort of connection. And the connection is like this. Right, so this transition fires, places the token here. This token will enable this transition. After this one, it fires. It's fine, right? Looks like it's okay. Will it work? Of course it will. But is there a problem? Yes, there will be a problem. The problem will be that we need this kind of feedback. Why do we need the feedback? We need it because enable this token enables, fire the transition, this token sits there, new token appears here, this token contributes to this transition, these two tokens cause this transition firing, right? Then the slave process begins eating our data, right? And after that, we have no idea when this transition will happen because this process can be fast or slow. Let's assume it's very, very slow. And let's assume that this guy is very fast. So after firing this transition, we have a token here. This transition may fire either immediately or later. There is no notion of time. If it happens immediately, then the token is here. If the master process is fast, it will fire this transition again, and again, and again, and again. And we will flood this place with tokens. Will be no tokens, then one token, 2, 3, 4. How many tokens accumulates there? I don't know. It depends upon how much faster this process is compared to this one. So it will not be a one safe Petri net. So it will be an error. The error is that it's caused by lack of knowledge how fast the other party is. So if the slave is very, very fast, then we are lucky. But if the slave is slow, then we need to have some indicator that the slave is finished. Otherwise, we will flood this place with tokens. So this indicator that the slave has finished means that we need to have a reverse channel. Inverse channel, it goes from here to there, like that. And only when the slave is finished, it will fire this transition. The token will be prepared to consume something new. This token from here will mark this, and together with this one, we will enable this transition and continue. Now let's do the same at the animation. This transition is enabled, fired. Now you see this is the token which we need to slow down. If the master is very fast, we don't want it to run circles before this guy is finished. So this transition will be waiting for the token here, and the token will arrive here only after the slave has finished. That's how it works. Meanwhile, this token together with this one enable this transition. Firing, disappear, appear. Now the slave may take 1 second or 1 hour or maybe 1 year. Doesn't matter how long it takes. It finishes, fires this transition. Right. And now the master stops waiting. You see? And now it's prepared to start the whole cycle of operation again. Rewind and play the game. So it will be very much the same operation here. Does it make sense?
Yep. Yes.
And after that, it's exactly the initial marking. So if you go back in time this position. We can start playing this again and again and again and again. Right, so what we looked at is the concept of concurrency. The concept of concurrency is defined on what? On places or transitions. We are talking concurrency, it's lack of order. We cannot define order on places because place is something which stores a token, right? Order can be defined on actions. Actions are transitions. So if we cannot tell whether two transitions will fire in one order or the other order because they are not connected with arcs in any way, then we have concurrency at hand. If it always happens that after one transition the other fires, then means that there is no concurrence. That's the concept of concurrence. All right, so what else we have here? Petri net definition, one safe Petri net model is the bit of mathematics. Not really, it's just mathematical definition, right? So it's not really a proof of any theory. Right. And after that, we went to the examples and introduced a very important concept of a handshake. The handshake is here, one way, the other way. So a connection between concurrent processes is always done through a handshake. The principle of handshake assumes that we have a direct channel and a feedback return channel. It's like in the army, you give an order to a soldier, and soldier runs somewhere, does the job, returns back and reports that the job is done. Why it is important in the army? Because reliability is not high, because the soldier can be wounded or killed in action, unfortunately, right? And then the job is not done, and you have to somehow confirm that the job is done, otherwise you will be acting on a false premise. So if you don't have this kind of indicator that the other party is infinitely fast, then you have to have this acknowledgement channel. They call it request and acknowledgement. And we will have this in the example of a pipeline later. There are more animations coming, of course. It's all based on handshakes. So we have learned plenty. Definition, examples, handshake principle. In the definition, in the examples, by the way, we also mentioned 4 words. It was fork join, fork create threads. It will be directly used in our programming. Join, it will be to reduce the number of threads. So one thread is waiting for the other to finish, reducing concurrency. Fork join, fork increase, join, reduce. Join is usually associated with waiting for another thread to finish. And we also have choice and merge. Choice, it's branch, if condition in C language. And merge, it's when you have several options by choice, but then the flow of your algorithm converges to the common flow. Does it make sense? Please have a look at the remaining multiple sets of slides and remaining lectures. So you may find something interesting. Here, the next one, building blocks. So it is about, say first, let's focus on fork and join and what we can build with this. Together with a handshake, we are arriving to the structure of a pipeline. The model of pipeline is different from a shift register, and the model is remarkable, basically. A pipeline capacity N means that you have multiple memory cells, and you put in them different objects, right? And then you are not just shifting them all towards the exit, right? But you allow them roll independently. So at first there was a gap between them, but then the gap may disappear. The important is that these objects never change the order between them. The order is always the same, but the distance between them can be different. It's a FIFO buffer. And they will arrive, they will emerge at the output in the same order as they arrived. Right? So it is a model, and you will see it looks like graph like that. Have a look, it's all there with explanation. And then there will be another one in the next lecture after that. Actually the same. So here we start with concurrency, and the second one here will be choice and merge, and will be the model of the asynchronous arbiter or mutex in programming critical sections. Again, there will be animation and tokens and critical sections shown there. It is quite interesting and essential. You have seen these models in my module, which is 8089. And then I said, okay, just skip the model, let's look at the algorithm. But here you will see the detailed description of the model and the animation of that. Many more examples and so on. And finally, here we are arriving to a different model. So I think that we'll talk about a different model, which is reachability graphs, the next time, probably tomorrow. Because now we need to finish. Reachability graph, it's a different model from a Petri net. It's a kind of a finite state machine, which captures all concurrency things, all effects of concurrency in Petri net. So in the Petri net, if you have two transitions concurrent to each other, this one first fires, right? Then this one, or this one first, this one second. So you don't know each other. In a reachability graph, you will be drawing this. That's the initial state, and my left hand, then right hand. Or we can do right hand and then left hand. So it will be a diamond structure, 1, 2, 3, 4 states in the finite state machine, which captures one possible trace and the other possible trace. So reachability graphs, it's a tool to enumerate a variety of scenarios in concurrent models. They're essential for understanding the meaning of concurrency and what it gives to us. It gives us improvement in terms of performance because you don't need to wait for whoever has to be before that. So just don't wait, and then everything becomes concurrent. But the difficulty with concurrency is that it complicates the behavior. Just too many traces are possible. Sometimes the number of possible traces increases exponentially. So it's exponentially compared to the number of threads. Your computer is doing something with multiple threads. You just take a snapshot, like with a camera, right? Or just freeze the process and just read the binary data from it and try to interpret. And if it is a single thread, then you'll easily find where in the algorithm it is. But if it is a concurrent system, then there are a huge number of options. And it all comes in the lecture on the reachability graphs. Have those. No, it didn't work. I clicked on this. I was hoping to see the preview. It doesn't show the preview, so I'm not going to open it in a special tool. It is something which you need to finish. And after that, we will be doing software implementation and software implementation, right? So these are mathematical models, and this is the software, and this is the software implementation of FSM. So it's this one, FSM, right? And this is the software implementation, concurrent programming of our Petri nets. So when you are writing the programs, you will be having those mathematical abstractions in mind, and you will be mapping one way and the other the properties of programs into the models and properties of models into the programs. It is important to see, to be able to see what properties, what concepts your program implements. So please finish the discrete event models, and after that we'll continue with software implementations. So tomorrow we'll be talking about the rest of the discrete event models and probably touch the software implementations. Right, any questions for today?
Professor,
Yes,
are we going to have lab sessions for this course?
yes.
All right.
In 2 weeks.
In 2 weeks.
Yes.
Okay.
So the plan is 2 weeks of theory and 2 weeks of coursework.
Got it.
And the next week we will distribute. I mean, it's me and Dr. Shah. We'll distribute the topics for the presentations and the sources. Actually, the source is, one of the sources is the book, which I ask you to download. Please download it. It's the book by Butazzo, can be downloaded from the campus only. Where is the book? Give me a second. It is in Canvas. Well, the link is on Canvas, but you need to download it from the authors, from the publishing house. Oh, missed it. Download Butazzo's book. Free if from the campus network. If away, then you can download, log in first into Unix Newcastle AC UK and then download it from there.
Okay, Professor.
So it is a PDF document, and it is the book on schedulers and scheduling. It's the theory of scheduling, and we will arrive to this at some point. And the point is here, scheduling and schedulers. And scheduling implement concurrent behaviors in the system, right? And with them, it becomes clear how concurrent programming works. And concurrent programming is based on discrete event models on Petri nets. So that's the idea of the whole system of the theory. So we are aiming eventually at that. So all this course with those lectures, it needs to be completed more or less this week. The next week you will be working with Feisha. So he has his own sets of slides. It's a lot. It's a lot, but not if you consider that between our sessions we have the whole working day, which is 8 hours of hard work, right? And this hard work is half of this work is probably watching videos, or maybe more than half. And some work is to try examples with a pencil and paper. So it is hard work at the moment. In the past, the assessment of this module was an exam for the theory and coursework report. Under the lockdown, it became just a coursework report, and many parts here now are pre-recorded, and it's probably the best. because the class are not overly assessed. You have more time to do things. And the theory in particular, scheduling schedulers, for most of you are assessed through the presentations, which will be happening in the week number 3. So we are in the week number 1 at the moment. So there will be some theory assessment anyway, but the major part of the assessment, it will be the report eventually. I don't know whether we are going to return back to the exams eventually the next year. This year, you see, there was no clarity whether we will go into the lockdown or not. And doing exams in the lockdown, it's quite difficult. The quality of exams is not high. It's better to have reports and presentations. Right, so thank you very much for coming.
Thank you.
I'll see you.
Thank you.
Thank you.
Thank you.
I'll see you tomorrow evening.
Thank you, Professor.
Goodbye.
Goodbye.